Hey guys, so in this video we're going to be going over piecewise functions. Piecewise functions is a topic that never gets enough recognition in the pre-cal chapter. So your pre-cal teacher probably didn't teach it well enough, and here in calculus they just expect you to know it already. So I'm not going to give you guys a crazy video on piecewise. I'm just going to give you guys enough so you guys can get through the next chapter, which actually requires some knowledge in piecewise. So let's get started. So here we have that piecewise functions are functions that are defined by different blank. So when you have a piecewise functions, the word here tells you different pieces of it are defined by different functions. So the blank there, we're going to have functions. Now, each piece of the function is actually cut and defined by its domain. So what I mean by that, let's jump right into example 1 and let's explain that real quick. So the domain of the function is what actually defines your piecewise function. So you may always wonder what you have here. Here you have like x less than 0 or like x greater than 0. This is actually the domain that defines your piecewise function. So here we have f of x is equal to negative x if x is less than 0. So what this means is that if x is ever less than 0, if you're ever going to input an x that is less than 0, you're going to use the negative x function. And on the bottom here, if you're going to use a number that is greater than or equal to 0, you're actually going to be using the x function. So that is what the piecewise function has and what the domain affects it. So now let's see how we would go from the function to graphing the function, right? Let's see how this piecewise function looks like. So what we do is we break down the piecewise into its left section and into its right section. So we're going to draw a table for the left side and for the right side. So we already have that right here. So the left table is going to cover our left values, and the right table is going to cover the right values, right? So we're going to be using the function f of x equal to negative x for the left, because that's the one that covers the values less than 0. And then for the right side, we're going to be covering f of x equal to x, which are going to include values that are 0 or greater. So here, when we're going to choose values for x for the left side, we're going to start off with 0, and then we're going to go to the left of it, right? So the first number to the left of 0 will just be negative 1, and then just negative 2. And then let's pick values to the right of 0 and at 0. So we start with 0, and then we have 1, and then 2. So you guys do see that I include 0 in both of these tables, although 0 is only included for the domain of one of them. 0 is only included right here on the bottom function on just x. But for graphing purposes, I'm going to include 0 in both tables, and you guys will see why. So let's now compute the y values for the left side of the function. So if we put 0 into negative x, right, that'll be like negative 0. That is just going to give me 0. If I input negative 1 into the negative x, that is going to give me positive 1. Now if I do that with negative 2, it's going to give me positive 2. So now we have the values for the left side of the function. And when we have 2 or 3 values, that's usually good enough. So now let's do the right values of this function. So if I input 0, I'm just going to get 0. If I input 1, I'm just going to get 1. And 2, I'm just going to get 2. So let's go right ahead into graphing these functions. I'm actually going to pick the left side to be blue and the right side to be, let's go with green. So let's make the right side green. Let me just erase this real quick. So we're going to say that the right side is green and that the left side is blue. Alright, so let's plot the values of the left side in blue. So we have 0, 0, but we're not going to draw a solid dot at 0, 0. We're going to draw an open circle. And the reason for that is that here we have that at 0 it is just less than 0. So 0 is not included in this domain. So we're just going to draw a hole at 0, 0. Then we're going to go to the coordinate negative 1, 1. So that's right up here. And then negative 2, 2, which is right up here. So that looks like a line, a straight line that goes through these 2 points. So I'm going to draw just that. And then we're going to draw the points on the right side. So we said that we're going to do that in green. So let's go ahead and do that. So now here I have 0, 0 again. But 0, 0 is actually included in the domain. So what this means is that I'm actually going to do a full dot, a shaded in circle at 0, 0. And then I'm going to go to my next coordinate, which is 1, 1 and 2, 2. Alright? So now we have graphed this function, and if you guys recognize from our library of functions, this is actually the absolute value function or the vagina function. So this is actually another way of defining the absolute value function, which is defined by negative x to the left of 0 and positive x to the right of 0. So this is actually the absolute value function that we have defined as a piecewise function. So the next thing I want to do is just compute the domain of this. If you guys remember that the domain of the absolute value function, that's fine, but let's do it. Let's say we had a piecewise function only scenario. So let's compute the domain of the left side. The left side, if you go to the leftmost point of this graph, you're going to be at negative infinity. Now as you travel to the right, you ask yourself, is it continuous at 0? Like do I have a hole there? But you had a hole in the beginning when I just drew the blue points because it wasn't included in the domain. But now that I drew the green points, you actually had it filled in. So there is no problem. There is no stopping. There is no asymptote. There's nothing that can stop you from left to right of this graph. So it is just from negative infinity to positive infinity, which is actually the domain of the absolute value function. So nothing here has changed. We have just expressed the absolute value function in a different manner. So now let's jump to some examples of this. But before that, I want to just remind you guys that this is a nice piecewise. This is a very nice piecewise. The reason why is because you have no problems because the left side matches the right. So a nice piecewise, let's call it PW, piecewise, is when the left kind of like equals the right. And what I mean by that is that right here at this point they join, right? That they just kind of connect from the left side to the right side. That makes it a nice piecewise. And in the practice problems after this lesson, I'm going to show you guys some not nice piecewise where things can be talked about that will affect you guys in the next chapter. But let's go to an example of a little more on piecewise. So a classic example on piecewise is going to be when they ask you to evaluate an x value, right? So they tell you find f of negative 1. So the thing with piecewise is that most people just don't know where to plug it in, right? So you have two functions, so obviously you can't have two answers because it's not a function, remember? You have one input, one output, that is a function. So if you have to input negative 1, the question is which function do I use, right? So which function do I use? And then this all becomes about domain because the functions are defined based on their domain. So negative 1 falls in the domain of x less than 1, right? So since it falls in the domain of x less than 1, I'm going to plug it into the function that corresponds to f to x less than 1. So f of x that I'm going to use in this case is negative x plus 2 when it's concerned with this value. So then I just plug in that value right away. So f of negative 1 is going to be equal to negative 1 plus 2. That's positive 1 plus 2. So I get 3. So the most common mistake would be like, oh, I don't know, I'm just going to plug it into the bottom function. Why not? But you have to realize that the domain tells you exactly where to plug it into. So that is the biggest mistakes with piecewise functions that I've seen. So next, let's go over another common mistake, which is in example B, where I have f of 1. So a lot of times people think that you have two values, right? Because you have x less than 1 here, and then you have x greater than or equal to 1 in the other one. So you're like, oh, they both have 1. So let me just plug it into both, and I'm just going to give them both answers. But you don't have two answers. You only have one. because 1 is only included in one of their domains. And which one is that one? The bottom function. So in the bottom function, which actually includes 1, is the one that you're going to plug in your f of 1. So your f of x that you use in this case is the bottom function because it includes 1 because of that equal to, and then you're just going to get f of 1 is equal to 1 squared, so it is just 1. So there, now you've computed f of 1. And there's another very common mistake when it comes to which one do I plug it into when it's the number that divides the function. Because 0 in this case, 1 in this case divides the function from its left side to its right side, right? So when you ask yourself, where do I plug it in at 1? You're like, man, I don't know. You look where it's equal to. So you look between the two inequalities and you ask yourself, where is it equal to? Then for part C, we just ask ourselves f of 5. So now we know that we just need to look at the domain, and where does 5 fall into? 5 falls into the bottom function, right? So we're just going to plug in 5 using f of x equal to x squared. F of 5 will just be equal to 5 squared. So that's equal to 25. So now we have evaluated values at this function. So the next thing that I can ask you about a piecewise function is find its domain, right? And later domain will take a whole different meaning that you guys don't even want to know about right now, but I'll let you guys get there. So here I'm asking you, what is the domain of this piecewise function? So there's two ways to look at this, right? But I'm going to explain it through a graph so you guys can visualize this now, and then later on you guys can just do it in your head. But let's start off with a graph. So let's say I want to know what the graph of this looks like, so then I can just visually see the domain. So let's plot some points. So I'm going to plot the points that I already have. I have negative 1 from letter A. I have negative 1, 3. See, this right here is a point, negative 1, 3. So I'm going to go ahead and plot that. Negative 1, 3. Then I'm going to plot the second point from part B, which is going to be 1, 1. So just 1, 1. And then I'm going to plot the third point from part C, which is going to be 5, 25. So 2, 3, 4, 5. Then I'm going to go up to I'm not really going to go up to 25. I'm just going to say it's like up there somewhere. Okay? So the question is, now, I know that to the left of 1 I have the equation of a line, if I recognize it from my library of functions, and to the right I have a parabola. But this is the idea, right? So I'm going to draw to the left of 1. So I'm going to put an imaginary line here. Well, not imaginary, I'm actually going to draw it at x equal to 1. Right? So to the left of 1, I'm going to just draw a line. So I'm going to draw it in blue. And also the line is going to go through, it's going to go through this point and this point. So I'm just going to draw a line through those 2 points. And I'm going to have a line. And then to the right of 1, I'm going to have a parabola because I can recognize that from my equations. So I'm going to connect this point right here to this point right here and just make it into a parabola. So now to the left of it is defined as a line, to the right of it is defined as a parabola. So now you see how it's in different pieces, it has different functions. So now the idea of the piecewise function makes a little more sense when we have a graph that's a little different than just an absolute value. Because in this case, you don't know a parent function to this, because there is no parent function to this. There's just like some ghetto function that you put in together between two functions that you already know. So now I'm going to erase this imaginary line that divides the graph into 2 parts. And we're going to talk about its domain. So we're going to talk about from left to right what is happening in this graph. What is the leftmost point of this graph? And we see a line that's going infinitely to the left. So the leftmost point of this graph is going to be negative infinity. How about as you travel to the right? As you travel to the right, you're going to go infinitely to the right because it's a parabola, and you're just going to go to x squared. Okay? So now checking the domain, we know that it's negative infinity to positive infinity. Now, how do you do that without a graph? Well, I can look at the domain of the top function and the bottom function independently, or the left function, the right function, depending on how you want to look at it. So negative x plus 2. This is a line, correct? So negative x plus 2 is a line. So a line has no restriction, so it's just from negative infinity to infinity. Now we ask ourselves, x squared, which is the bottom function, right? The bottom function. Does that have any restrictions? It's a parabola, and if you guys remember, parabolas are just negative infinity to infinity. So since they're both negative infinity to infinity, there's no restrictions in either domain. The total domain, which you guys should remember this from computing domain, the total domain is just going to be negative infinity to infinity for a whole function. So there's two ways. You can actually just put the graph together, or you can actually just compute the domain of the left side of the function and the right side of the function. So there's two different ways. So now we're going to be doing some practice on how this piecewise functions can get a little tricky. So see you next time.